Okay, so we have the components on the top, and then the second vector and that's how you find the volume of a parallelepiped. So example, find the volume of parallelepiped determined by 6, 3, -1, 3 vectors, and 0, 1, 2, and 4, -2, 5. So here's a formula. However, it is a lot faster if we use this direct formula. So you write all the components in order. So we're going to have 6, 3, -1, 0, 1, 2, 4, -2, 5, just like we did before, and evaluate, reduce it to 2 by 2, you should get 82. Now, equation of a line, L, passing through a point P0 and parallel to vector V with components A, B, C. So we write this parametric equation. You start with the coordinates of the point, x0, y0, z0, and we add a parameter. A t is a parameter. So we call this parametric equation of a line. Parametric equation of a line. All right. Now we also have scalar equation. Now I'm going to give you a scalar equation. A scalar equation of a plane through a point, fixed point, we'll call it P0, with coordinates x0, y0, z0, with normal vector. So normal vector is the vector perpendicular to the plane. The normal vector n with components a, b, c. A picture. Here's the plane and fixed point on the plane, and the normal vector sticking out perpendicular to the plane. So here's the equation: a, x minus x0 plus b, y minus y0 plus c, z minus z0 equals 0. Example, write equation of a plane that goes through a point. Write equation of a plane that goes through 6, 3, 2, and it is perpendicular to vector with components -2, 1, 5. So that's the normal vector. Okay, so we have infinitely many normal vectors. You pick the simplest one. So this is basically the A, B, and the C. So we start with those coordinates, and then we do x minus 6 plus, this is 1, so that'll be y minus 3 plus 5, z minus 2 equals to 0. After you simplify this, you can write the equation in a standard form. And that's it. Another example. Write equation of a plane. Write equation of a plane passing through 3 points. P, 1, 3, 2. Q, 3, negative 1, 6. R, 5, 2, 0. So 3 points determine unique plane. You need to determine the vector PQ. And we'll call this vector A. And after you use the initial and terminal point, you subtract. So you're going to do 3 minus 1 to get 2. And then negative 4 and 4. So this is a vector on the plane. Then the vector PR is also on the plane. We'll call it B. And in the same way, find the components on the vector by subtracting 4, negative 1, negative 2. And our vector, the normal vector n, is actually the vector product of those two. So if you multiply two vectors on the plane, that product, the vector product, is a vector perpendicular, and that's our normal vector. So we know how to do this. IJK, 2, negative 4, 4, and 4, negative 1, negative 2. We know how to expand this. And so that is 12i plus 20j plus 14k. So our vector n has components 12, 20, and 14. And now we can write the equation of the plane. We have everything. We have the normal vector, and we have the pick one of the fixed points. And now if you simplify it, you'll get 6x plus 10y plus 7z. This is 7z equals 50. All right. So I'm going to let you work on chapter 6 on your own. So review 6.6, 6.7, 6.8 on your own. I have assigned problems on the online homework from those sections. And now chapter 7, we have a lot of formulas I like to write down for integration. So integral x to the n dx. Everybody knows that formula at all times. So it's true for every n not equal to negative 1. A new formula from Calc 1, so it's not new. ln absolute value of x. Don't forget plus c for all indefinite integral. This is the easiest formula in calculus. Whether you integrate or differentiate e to the x doesn't change. However, if the base is something else different than e, then we have to make adjustments with that ln a. The trig functions, negative cosine x here, and integral of cosine is sine. If you ever forget those, you write your differentiation formula and then reverse them. So secant squared, I cannot write just about anything after the integral because it's a lot harder to integrate than to differentiate. So these are selected formulas that we know from differentiation. Okay, with our techniques, however, we can increase this list of formulas. All right, so we know those from Calc 1. These should be all familiar, but it's good to review them. We have a few new ones. So here's the new one. Or perhaps you did it in Calc 1. So you write, this is a problem that you had solved for integral of tangent, but it's a good idea to remember it. It's useful. The cotangent is similar So it's ln of sine. And here's the new one, 1 over x squared plus 1 dx. This is the inverse tangent. And now we've done a problem where instead of 1, we have a squared. And if you forget that formula, it's easy to derive it using substitution. And one last one, 1 over square root of a squared minus x squared dx. This is the arc sine x over a. So if you substitute a equals 1, then you're going to get the arc sine formula. All right, time for examples and to review techniques, integration by parts. T squared e to the t dt. So e to the t is a function that doesn't change. So we'd like to keep it behind the differential, behind the d, because the derivative of e to the t is e to the t. So nothing's changed. So we do integration by part. I should probably write the formula here. So integral u dv is equal to uv minus integral v du. So we switch the u and v to help us with the integration. So here I'm going to multiply u and v. So in this case, it's going to be t squared e to the t minus, now I'm switching them, e to the t d t squared. Okay, so now I simplify this because I know the derivative of t squared is 2t dt. And now I can pull the 2 on the front and I have e to the t times t dt. I have to do integration by parts again. We reduced the power, it was t squared, now it's t. So things improve, but we're not done. So I'm going to write this as t derivative of e to the t. And I'm going to do integration by parts again. Because the integration by parts has two terms, I'm going to put brackets. So multiply these two, minus, and switch them. Okay, I'm going to distribute here. Minus 2t e to the t plus 2 integral e to the t dt. I can integrate this, and we're almost done. Plus 2 e to the t plus c, one constant for the end. Now you can factor e to the t if you wish. It's good enough to leave it like this. Now trig substitution is what we use for integrals that have trig functions. So example, integral sine to the fifth x cosine squared x dx. So we're reviewing chapter 7 here, still chapter 7. We have odd and even powers, a mixture of odd and even. So I'm going to use the substitution where cosine x is u. So cosine is the it's the even power. I'm also going to break down one of the signs. So it's going to be sine to the fourth x, cosine squared x, and then d cosine x. The derivative of cosine x is sine of x. So now with the substitution, everything is good except for the sign. So sine squared of x is 1 minus cosine squared of x, which is 1 minus u squared. I have sine to the fourth x, so that would be 1 minus u squared squared. So we're ready to substitute. I'm going to have 1 minus u squared squared. Cosine squared x, that's just u squared du. So this is not a difficult integral. We can solve this, and in terms of, I would FOIL, distribute, and you would have at the end negative u to the third over 3 plus 2 u to the fifth over 5 minus u squared over 7 plus c. Go back to what u was. That was cosine of x. And this is our final answer. Don't forget plus c. A few trig formulas. There are helpful identities. We call those Pythagorean identities. Pythagorean identities are these three formulas. One, let's start with the first one, the most popular one. Sine squared plus cosine squared of x is 1. And then 1 plus tangent squared of x is secant squared. 1 plus cotangent squared of x is cosecant squared of x. We also have formulas for reducing the degree. So if I have sine squared of x, we have a formula for that, reducing the degree. The angle is double, which is okay. We can integrate that. And cosine squared of x is the same, except it's 1 plus here. Okay, so we use this whenever we integrate square of sine, square of cosine, or any even power. So we have also trig substitution table of trig substitution. In your textbook, you have 3 separate expressions. So we have, I'm going to make like a table here with the expression, the substitution, and the identity we use. Identity or formula. So in a case where you have to integrate an expression like this, a squared minus x squared, a can be any number, so it can be 1 or 2. The substitution we use here, it's x equals a sine theta. And in order to do that, we have restriction for theta between negative pi over 2 and pi over 2. That has to do with the inverse being defined. The identity we use here, 1 minus sine squared is cosine squared. Another type of expression is the same but with plus, and here we use the substitution a tangent theta. The theta here is between negative pi over 2 and pi over 2, but not equal. We know the tangent is not defined when theta is pi over 2. The identity we use here is 1 plus tangent squared of theta, which is equal to secant squared of theta. And the third type is x squared minus a squared. We use the substitution x equals a secant theta. And here the angle theta is from 0 to pi over 2, or from pi to 3 pi over 2. The identity, secant squared minus 1, is equal to tangent squared theta. So here's a quick example. For this type of trig substitution, I have to integrate square root of 9 minus x squared over x squared dx. So I'm looking, and this expression looks like the first expression. Okay, so the substitution I'm going to use is x equals 3 sine of theta. A is 3, of course. So the x is 3 cosine theta d theta. And we're going to substitute right away. So that's equal to integral square root of 9 minus 9 sine squared theta over 9 sine squared theta. And the x is 3 cosine theta d theta. So that becomes integral. After we take square root, 1 minus sine is cosine. So that's going to be 3 cosine theta on the top. And the bottom, 9 sine squared theta times 3 cosine theta d theta. We multiply the 3 and the 3 and cancel. So this, and this will cancel. And what's left on the top is cosine squared theta, and on the bottom, sine squared theta d theta, which we know is cotangent squared d theta. And we have a formula, a trig formula, that can convert cotangent squared to cosecant square theta minus 1. And we can break this down into two integrals, cosecant squared theta d theta minus 1 d theta. And that is a formula. So that's negative cotangent theta minus theta plus c. All right. So that was chapter 7. And review on your own 8.1. And then I will do a little bit of chapter 10. So chapter 10 would be 10.2, 10.3, 10.5, 10.6. I have an example from chapter 10 here. Chapter 10. Example where you have to find the radius. Find the radius and interval of convergence. Okay, I think that's chapter 11. Yeah, this is chapter 11. All right. I have this series, it's alternating, and n is from 0 to infinity. So I'm going to use the ratio test, taking the ratio of the two consecutive terms and substituting. That's going to be negative 3 to the n plus 1 power x to n plus 1 over square root of n plus 2. And I'm going to reverse the nth term. So I'm going to have square root of n plus 1 on the top, negative 3 to the n, x to the n. Then I'm going to rewrite some things in order to cancel. That's going to be negative 3 to the n times negative 3, x to the n times x, and nothing to do about the square root. Copy everything else. And we can see now that we can cancel x to the n and negative 3 to the nth. So what's left? N is positive, so we don't need absolute value. So I can do 1 square root n plus 1 over n plus 2. And absolute value of negative 3 is 3, so I can put that, and x needs to have an absolute value. So if n goes to infinity, what happens? We should probably divide by n first and then take the limit. So let's divide by n, top and bottom. So that would be 1 plus 1 over n, and here 1 plus 2 over n. So now this 1 over n goes to 0 and n goes to infinity, and this goes to 0. So if n goes to infinity, this limit is 3 absolute value of x. So we want this number, that limit, to be less than 1 to have convergence. So that's equivalent to absolute value of x less than 1/3, and the radius of convergence is 1/3. The interval of convergence is negative 1/3 to 1/3. About the boundary points, we need to check each one separately. So for a equals negative 1/3, what is the series that we get? Substitute a with substitute x with negative 1/3, and you're going to get 1 over square root of n plus 1. N is from 0 to infinity. You can expand it so you can see the behavior. And this is a p-series with p equals to 1/2 less than 1, so it's divergent. So for a equals to 1/3, the other boundary point, our sum looks like this, negative 1 to the n over square root of n plus 1. So it's alternating. And we know this is convergent. So that by alternating series test, the interval of convergence is negative 1/3 to 1/3 including. So including the upper bound 1/3. All right, so we just used the ratio test. The root test is similar. We have 3 cases. I just want to remind you about the part when we find convergence or absolute convergence, and that is you take the limit of the nth root of the absolute value of the nth term, and if that limit when n goes to infinity is a number less than 1, we have absolute convergence and therefore convergence. So example, using this test for convergence. Test for convergence, and the series is 2n plus 3 over 3n plus 2 to a power n. N is from 1 to infinity. So we take the nth root of the absolute value, but we don't need absolute value because n is positive. We let n goes to infinity. We can divide by and, so it's clear. Divide by and. So 2 plus 3 over n, 3 plus 2 over n. Let n go to infinity and you get 2/3, which is a number less than 1. So our series is convergent. Okay, a few power series we want to remember, very useful. The geometric series one. The sigma notation, that's x to the n. So this is convergent when absolute value of x is less than 1. And then we had e to the x to the n over n factorial. So we remember those because we use them to solve other problems. So they're kind of fundamental. 1 plus x factorial, 1. No, this is x to the 1 power. X to the 1 power, 1 factorial plus x squared, 2 factorial plus so on. And this is convergent for every x. So the interval convergence is all real numbers. And the binomial one was 1 plus kx plus k minus 1 over 2 factorial x squared plus and so on. This one, the absolute value of x is less than 1. So example, find 4th degree Taylor polynomial find 4th degree Taylor polynomial of f of x equals cosine x centered at x equals 0. And so we know, or a equals 0 if you want to, then that's the Maclaurin series. When Maclaurin series, the Taylor series at 0. So our function is cosine x. In fact, we've done this in our notes earlier. So we can write this polynomial as a series at 0. And we can expand it. So that's f of 0 plus f prime of 0, 1 factorial x plus second derivative of 0, x squared plus third derivative, x to the third, and so on. So let's start with f of x being cosine x. F of 0 is cosine 0, which is 1. F prime of x is negative sine x. F prime of 0 is 0. The second derivative is negative cosine x. The second derivative at 0 is negative 1. The third derivative is sine of x. The third derivative at 0 is 0. The fourth derivative is cosine x, and you see the pattern here. The fourth derivative of 0 is 1. So when you substitute this and you want a 4th degree polynomial, so we can say cosine x is equal to the sum of its Taylor series. So 1 minus x squared over 2 factorial plus x to the 4th, 4 factorial, plus a constant c. So that concludes the review section.